Large language models are often treated as opaque black boxes. We type a prompt, and a coherent response emerges. But to build reliable systems, we must understand the internal geometry powering these engines. Prior to 2017, artificial intelligence processed human language sequentially using recurrent neural networks, or RNNs. These architectures read and process data one step at a time, keeping a running memory of what they have seen. The critical flaw of the RNN is this sequential design. Because it processes left to right, information from the beginning of a long sequence degrades. By the time the network reaches the end of a paragraph, the initial context has often faded. In 2017, the Google Brain paper, Attention is All You Need, introduced a new model that completely discarded sequential processing. This transformer architecture changed the mechanics of NLP by evaluating all words in a sequence simultaneously. This simultaneous processing allows the model to track long-distance dependencies. A pronoun at the end of a document can connect directly back to a noun on the first page without losing the signal. Moving from sequential bottlenecks to parallel processing is the foundational physics that made modern language models possible. Large language models convert raw text into high-dimensional spatial geometry. The initial step is tokenization, breaking raw human text into discrete numerical units called tokens. Tokens are mapped into a dense, multidimensional vector space through embedding. In this geometry, physical proximity equals semantic similarity. The spatial relationship between man and woman is identical to the distance between king and queen, allowing for direct algebraic operations. While older models used static embeddings with one fixed coordinate per word, modern transformer architectures use dynamic contextual embeddings. For instance, the word bank in the phrase riverbank shifts to an entirely different set of spatial coordinates than the word bank in bank account, based on the surrounding sentence. Embeddings translate the nuance of human language into precise, deterministic mathematical coordinates. This raises a mechanistic question. How does a token dynamically update its meaning based on surrounding words in a matter of milliseconds? Self-attention calculates relevance using queries, keys, and values. The query asks for specific context. Keys are searchable labels representing all other tokens. The model compares the query against every key to find a match. The matching value is extracted, updating the token's final state. Modern language models perform this exact calculation dozens of times simultaneously through a process known as multi-head attention. Different attention heads track different linguistic layers in parallel. One resolves pronouns, another monitors grammar, and a third tracks semantic tone. Attention allows the model to weigh every word against every other word, producing a mathematically refined representation of the text without human intervention. Moving to the macro architecture, the original transformer branched into distinct paths based on how this attention is routed. The first path led to encoder-only architectures, such as BERT. Encoders use bidirectional attention. They scan an entire text sequence from both directions simultaneously, considering the full context of a document at once. This bidirectional context makes encoders ideal for classification, semantic search, and document clustering. The second path created decoder-only architectures like GPT and Llama. Decoders process data autoregressively, strictly left to right. They mask all future words, forcing the model to predict the next single token based only on the preceding context. This autoregressive design is why decoders excel at generative tasks and conversational AI. This diagram illustrates the final path, encoder-decoder models like T5. Here, a bidirectional encoder passes contextualized embeddings into an autoregressive decoder, allowing the system to translate an input sequence into a new output. Business utility is dictated by architecture. Choose encoders for understanding, decoders for creating, and encoder-decoders for sequence transformations. Architecture is only half the equation. The scale of the system is the other. The chinchilla scaling laws provided a framework for how we train and size these models. This chart shows the core finding. Early models were often too large and undertrained. The volume of high-quality training data matters as much as the parameter count. Successes like Llama 3 outperform larger competitors because they are efficiently sized models, saturated with massive amounts of data. Efficiency and data density are what unlock emergent behaviors like chain-of-thought reasoning. Understanding the engine dictates how you implement it in a production environment. Organizations trade off customization against cost and time. Prompt engineering allows rapid prototyping with zero architectural changes. Fine-tuning permanently alters a model's domain behavior. And retrieval-augmented generation, or RAG, is the strategic middle ground for querying proprietary data. While fine-tuning permanently alters internal weights, RAG passes external documents into the attention mechanism at runtime. However, the QKV attention mechanism suffers from a lost-in-the-middle phenomenon when oversaturated. So even with large context windows, the density of data in the prompt matters. Every pipeline step is linked. Tokens map to embeddings, contextualized by attention, inside an encoder or decoder. Use this architectural framework as we move to the next module, where you will architect and build your own enterprise RAG systems.